Okay, so like I said, we have really covered all the physics, the quantitative part of it. So I'll just mention a couple of practical examples and analyze on a macro scale, on a high level, what is the physics going on. In particular, let's look at what goes on in a roller coaster, going through a loop-the-loop track, and look at driving around a bank. Okay, and by driving around a bank, I don't mean the bank robber going around to withdraw money. What I mean is it's going around a curve, and it's a bank curve. Okay, so in a roller coaster case, right? So this is a very standard track you have. So what's going on over here? What if you are a roller coaster engineer? You probably are curious to find out what is the minimum speed that you need to be able to not have the car fall down. So what happens is the car is going to be upside down over here. So you want to find out what is the V min that it has right over here. More correctly is you really want to find out what's the V min here so that it can achieve the full loop. But we'll do one thing at a time. We'll find out what the minimum speed is required over here first. And then actually next week we'll talk about how do you translate that prediction. Let's say if I need it to be at 3 meters per second over here, then what is the speed it has to be at here in order for that to be 3 meters per second over here. All right, we'll focus on this part first. Now draw the free body diagram. What's in contact with it? It's the wheels on the track, right? That's the only thing in contact. So that will be a normal force. And which way is the normal force? If you imagine going around it very fast, right? Which way is the normal force pushing? Is it pushing the roller coaster out of the circle or inside the circle? The normal force is pushing it inwards, right? So that's the normal force. Anything else? There is also gravity, right? So there's a weight, and that's it. Okay, so that's the contact force, and that's non-contact force. And what is the what is the analysis over here? What's the centripetal force? So the centripetal force is N plus W. Okay, so you might be curious, what is the normal force? And you can go and calculate that. The normal force, actually, let's plug in mv squared over r first, and we'll plug in formulas for everything, right? So we have a formula for W, we have a formula for centripetal force. And remember, this is one way to go about it. If you find that confusing way to think about what are the forces that is causing the centripetal motion, you can always think about it in terms of Newton's second law, which is in fact actually more rigorous. This is some sort of shortcut if you can view it that way. So you start with Newton's second law and say, hey, I'm interested in the centripetal acceleration. So what accelerates in the centripetal direction? And I need to put in all the forces that's going to the center. So I know that it's accelerating towards the center, and what is the forces that's causing it to do that? Well, this is v squared over r, and what are the net force towards the center, right? The direction of this is to the center, the direction of this must be to the center. So it's N plus W. As you can see, I get the same conclusion. Okay, so both ways work, whatever you're more comfortable with. This is generally a step quicker, so either way, right? So the normal force is equals to mv squared over r minus mg. Let me just pull out the m since it's common, like this, right? So you see, if I increase the speed, notice the radius is fixed, g is fixed, so I'm only allowed to play with v. So if I increase the v of the car at this point over here, it will increase my normal force. Does that make sense, right? If it goes around really fast, you feel pushed towards the track more, right? So, or in other words, the track is pushing on the car more. It's Newton's third law, it's the same thing, right? So the force on the track on you will be more if you go around faster. Okay, so that makes sense. What's the minimum V? Well, the minimum V is, so you want to put minimum here, then that means the smaller that is, the smaller. So we flip the arrow, right? The smaller the V, the smaller the N. What's the smallest normal force? It will be 0, right? Can it be less than 0? If it's less than 0, it's pointing upward, but that doesn't happen, right? The normal force cannot push the car that way, it only pushed the car that way. So again, you can set this to 0 and then solve for V-min. So that's the physics over there. The normal force 0 meaning sort of over here, it's basically not pushing back on you at all. You're almost just at free fall, right? That's W is the only force existing if N is 0. So you have a momentarily sort of free fall experience when you are over there, okay? So I should say this is also somewhat idealized or somewhat abstract from the real life situation. In real life situation, things are not as dangerous as it sounds because roller coasters usually have wheels on top and bottom of the track, sandwiching the wheels. So it actually sort of clamps the wheel along the path, even if there's friction and there was a particular day, there was dust on the rail, that it goes slower, the car will never actually fall down. It's always going to climb on there. But just as a theoretical exercise, it's good too. So no worries if you have a fear of roller coaster. They should be designed to be perfectly safe, all right? So how about a car driving around a circle? In fact, let's split this into two, right? Around an unbanked circle and a banked one. Okay. So what's going on when you have a car going around? Well, this is the top view. It's going around. At this moment, the tangential velocity is going here. And we know there needs to be some sort of centripetal force to accelerate it this way when it goes around a circle. So assume it's not a bank, so this is completely flat, right? Flat ground. What is providing that? What is providing the centripetal force? In other words, if I use Newton's second law to write down ma equals to F net, right? There's some force that is towards the center, and it's accelerating towards the center, I know, because it's going here with a constant speed, let's say, right? Uniform circular motion. So there must be some net force. What is that? What is the net force that is providing this way? Well, you draw a free body diagram. You ask yourself what's touching it. Well, let me draw it like this. And it's going around a circle. Excuse me. So I can't really draw in 3D, right? So it's going to go this way. That's what I mean. And this is sort of the back view of the car. It's going forward. Yeah. So what's the free body diagram? Well, it's in contact over here. So there is a normal force. There is its own weight. And what else? Should we care about friction? Now let's think about it. What happens without friction? Are you able to make a turn without friction? No, because friction is what, so it turns out in this case, it's not, I cannot even ignore friction because if I don't have friction, there's no way I can turn, right? It'll just continually go tangentially, right? In the tangent to the path. So yeah, what is providing the normal force is the friction, okay? So is the friction going this way or is the friction going this way? Question number one. Question number two, is it static friction or kinetic friction? Okay, both of them may surprise you because if you sit here, you might think, hey, I feel like there's something pushing me outwards. Probably that's where the force is. That's where the term of centrifugal force comes from. However, centrifugal force is not real. There's no centrifugal force at all. Centrifugal force is a class of force, what's called fictitious force. Force. So it's almost fiction. It's a force that you feel as a result of a frame of reference that is changing directions, okay, or non-inertial, what's called. So you're not at a constant velocity and you feel like there's an extra force, but that's not real. You need to ask yourself, the friction always opposes motion or tendency of motion, okay? So if I don't have friction, which way will the car move? Well, the car will move away from the center, right? The next moment it will be here. So that will be further away from the center instead of where it should be, right? It should be turning, but it will be here without friction. So friction must be pointing towards the center, okay? And the next question you ask is, is it static or kinetic friction? And this is again trivial, non-trivial, because you might think it's kinetic. However, you need to ask yourself in which direction. Is it initially, so at first it has a tangential velocity going this way. Is there any velocity in the radial direction? No, there's no radial direction. So if you don't have friction, there's a tendency to move the next second to move away, right? There's a tendency to move away from it. So friction is actually counteracting the tendency to move away from it. So that is actually a static friction. It's not, if it's a kinetic one, it's continuously sliding around it, right? So another way to think about it is, remember, kinetic friction is if this box is accelerating downwards, the kinetic friction, it's a sliding issue, right? There's a constant sliding through this direction, but here this is not slipping. This is not sliding in the radial direction. It's just causing it to go in, right? It's almost like a box over here. If you push it, right? If you push it, there's a friction backwards, and that is the static friction, because there's no sliding. At the moment there's sliding, it becomes a kinetic one. Okay, so it's not sliding radially, and that sometimes any questions will sometimes say without slipping. So these are the keywords to look for. Without slipping, then it means that it is a static friction. That is what's causing it to go in a circle. Okay, so probably the most intricate thing is you can put 2 and 2 together, put all of these concepts together, and try and analyze a car going around the banks. So this, if I look at a cross section over here, this might be actually banked, right? So this is the car from the back. So it's going around like this. Okay, so there's an angle over here, and you can be asked, if I don't have any friction over here, can I cause it to go in a circle? Okay, so this time I have no friction. Now let's look at a free body diagram. Do I need friction in this case? Well, there is a normal force from the contact over here. That's nothing to do with friction, right? Friction will be not normal to the contact. There is also its weight, like this. And now I see something that's not at an axis. So I will resolve that into its components. Right, so I have ny and x like this. And what I should see is, if I want no friction and it sort of stays at this altitude, then I need this to balance this, so it does not accelerate off the bank or into the bank, right? However, I have an unresolved force over here, sort of unaccounted for force. So that must be the net force. But that is precisely pointing towards, right? That's the bank. It's hard to draw like this, right? So it's going around like this, right? So the nx is the force that is actually causing it to go in a circle, right? So the centripetal acceleration is caused by nx. So this is v squared over r. Okay. And you can look at more in the textbook examples. It's in chapter 5, and I think you are well equipped to solve all these problems with circular motions.